All right, let's dive in. Uh, in section 7.3, our main focus here actually isn't listed in these two things. Our main focus in section 7.3 is actually the normal curve. But in order to study the normal curve, the things we're going to talk about are standard deviation and the 68, 95, 99.7 rule. We're going to start out talking about standard deviation. And there is a formula for standard deviation that may look a little intimidating at first. That's okay. We're going to talk through every single piece of this to make sense of it. And then we're going to practice using it. So here goes. Standard deviation tells us how spread out a data set is. If the standard deviation is a small number, then the data is not very spread out. If the standard deviation is a big number, then the data set is more spread out. And the way that this can be used is if we have two different data sets that we want to compare to each other and we want to know which one's more spread out. Let's say if I had two different Math 123 classes and I wanted to know, were all these test scores grouped closely together or were they spread out all over the place? One of the ways I could find that out is by using standard deviation. And whichever data set had the higher standard deviation, those test scores would be more spread out. So it follows what our logical impulse would be, that a higher standard deviation means the data set is more spread out. We're going to find standard deviation using a formula. And that formula looks like this. Now, at first glance, that's a little intimidating. So we're going to talk through every little piece of this formula. What we have here is the standard deviation is found by taking the square root of all that stuff. Let's take a look at that stuff. First, we can see that X bar is in there. And it's in there a whole bunch of times, actually. We have X bar a whole bunch of times. And we already know what X bar is. X bar is just the mean. So we're going to need to find the mean of the data set, and we're going to use it over and over and over again. And okay, that takes care of all of these. All right, what else do we have? We have that n down there on the bottom. This n down here, that n is the number of data points. And then the only thing left that we have not talked about yet is this x with a little 1, x with a little 2, x with a little 3, all the way to x with a little n. And what those are our individual data points. X with a little 1, like that. X with a little 1 is pretty clumsy and not very formal. Technically, what that is x with a subscript of 1, and it's our first data point. The 1 indicates that this is the first data point. Now, saying x subscript 1, x subscript 2, x subscript 3 would get old really fast. So instead, what we'll say when we're talking about x with a little 1 next to it is we will call that x sub 1. So we'll say x sub 1. When we say that we are not saying x of 1, we are saying x sub 1, and it's short for subscript. So x sub 1 here, that's our first data point. And then x sub 2 is our second data point. X sub 3 is our third data point. And then because the formula has to be flexible enough that I don't know how many data points there are going to be. Maybe there's 4, maybe there's 5, maybe there's 12. However many data points there are is called n. And so this down here is our nth data point, the last one, however many there are. So that's what that x sub n is at the very end. Right now, this is strictly theoretical. We're just looking at a formula. In a second, we're going to look at how to use this formula, how it works when we put numbers in. But before we do that, I want to give you a chance to ask any questions you have about what it is you're seeing here. All right, if all those symbols and all those characters make sense, we're in great shape to move forward to take a look at how this thing works. There isn't, you'll notice nowhere on here is an x, Zara. There is x sub 1, x sub 2, x sub 3. There's nowhere that there's just an x. So x sub 1 is the first data point, x sub 2 is the second data point, x sub 3 is the third data point. But these things do represent our data points. Cool. All right. So if we were asked to find the standard deviation for this data set that's 42, 47, 61. Now, I realize that's a very small data set. And in the real world, data sets are going to have a lot more numbers than that. But because you're going to be in a position of calculating standard deviation by hand, and the more data points we have, the bigger the formula gets, we're going to keep things relatively small and relatively simple. It's more about the process than the actual numbers we're using. So if we want to find the standard deviation for that data set, we can see right away that I have 3 data points, x sub 1, x sub 2, and x sub 3. And that's all my data points. And I can also see that n is going to equal 3. You don't have to label them like that, but I don't see what it hurts, and it helps keep us organized when we go to start plugging stuff in. So now I've got this. The other thing I'm going to need, so I've got x sub 1, x sub 2, x sub 3. That's all the way to the end. I've got n. What I need is the mean. So I'm going to have to find the mean of this data set. So we can do that. I'm going to need the mean, and that's going to be 42 plus 47 plus 61 divided by 3. Let's see what that gives us. 42 plus 47 plus 61, that's 150 divided by 3, which is going to be 50. So now I know the mean is 50. All right, now let's put this formula to work. What I'm going to do is I'm looking for the standard deviation, and I'm going to plug in to this formula here. And I'm going to get the square root, something that, an abbreviation that is common to use for standard deviation instead of typing the whole word out is a symbol that looks like a cursive lowercase o. It's actually a lowercase Greek letter sigma. And so we can use that as an abbreviation for standard deviation. All right, so standard deviation is going to be square root of, okay, here it goes. Now look at my formula here. I have x sub 1, that's 42, minus the mean, which is 50, squared, plus x sub 2, which is 47, minus the mean, which is 50, squared, plus x sub 3, which is 61, minus the mean, squared. And that's all divided by however many data points we have, which is 3. So we've plugged in everything. Before I go forward, I want to give you a chance to ask any questions you have. I want to make sure that all those numbers in all those places make sense before we go forward. What we've got here is x sub 1 minus the mean squared, x sub 2 minus the mean squared, x sub 3 minus the mean squared. And that's all our data points. The 2 at the top is -2. I'm not sure I understand your question, Nicole. We are subtracting the data point minus the mean and then adding. Subtract data point minus the mean and then add, subtract data point minus the mean. Dash on top of the second x. Oh, that is our abbreviation. X bar is our abbreviation for the mean. So when you see X bar like that, that's an abbreviation for the mean. Perfect. Very good. Excellent question. Excellent question. Very good. And that's exactly what I want you to do. If you see something you're not sure of, make sure you ask it. Okay, now we need to simplify this, and we'll have our standard deviation. It looks like a whole lot going on, and there kind of is, but honestly, it cleans up pretty quickly. And I'll show you what I mean by that. So, all right, as we're working through this thing, let's see, standard deviation is going to be square root of, all right, well, 42. Oh, order of operations, little reminder. Parentheses, exponents, multiply, divide, add, subtract. Please excuse my dear Aunt Sally. If we have any work to do inside parentheses, that has to go first. And here we do. We've got work to do inside these parentheses. So we're going to do that first. Once we're done with that, then we'll do exponents, and we'll go from there. So 42 minus 50, that's going to be negative 8. That's going to need to be squared. 47 minus 50 is negative 3, and that's going to need to be squared. And 61 minus 50 is 11, and that's going to need to be squared. And the whole thing's divided by 3. All right, now we do exponents. So we're going to do our squaring next. And I'll have standard deviation is square root of negative 8 squared. Let's take a little second and talk about that. If any of you remember intermediate algebra, it's not something that we do as a course anymore, but if it was a long time ago and you took it from me, this would have definitely been a question you would have seen. The idea is that those two are not the same as each other. This one on top, because we do exponents first, this would be 8 squared, and then the negative would go in front of it. That would be negative 64. In contrast to that, the one on the bottom, these parentheses tell us something. These parentheses tell us that everything in here is getting squared. And so what we're doing in this case is we are doing negative 8 multiplied by negative 8. The 8 times 8 is 64, that's true, but negative times negative gives us a positive 64. So these two things are different from each other. With no parentheses involved, negative 8 squared gives us negative 64 as a result. In contrast to that, negative 8 squared gives us positive 64 as a result. It's a really important difference to note. Those parentheses around that negative 8 are really important. They mean something, they matter. They're telling us when you multiply this, when you do this squaring, you're doing negative 8 multiplied by negative 8. And what that does is that gives us a positive 64. Similarly, negative 3 times negative 3 gives us a positive 9. 11 times 11 is 121, and that's all divided by 3. When I say this cleans up in a hurry, this is what I mean, because we had a pretty complex looking thing, and just a couple of steps later, we're down to something that's much more simple. At this point, we have to remember that this division bar tells us do everything on top, do everything on the bottom, divide last. So we're going to need to add those 3 numbers that are in the numerator there. And we'll get that the standard deviation is square root of, let's see, 64 plus 9 plus 121. Looks like 194 over 3. Now we finally do the division. 194 divided by 3, and I get 64.66666. And I'm going to keep that on my calculator. And I only have one thing left to do, and that's take the square root. Square root's going to be an important function for us here, so you're going to want to make sure you can find your square root button. It might just be a symbol like that. It might be a symbol like that with an X under it. It might be a symbol like that with a squared over here and an X under it. Any of those will mean square root. And what we're finding here is what number multiplied by itself would give us 64.6666666. Please don't forget this last step of taking the square root. It's an important part of things. And we'll take the square root. And I have standard deviation is 8.0415. And that keeps going. I didn't say where to round in here. How about we round to the nearest hundredth? What the heck? We'll round to the nearest hundredth. There's a 4 in that spot. We look one place to the right. That's 4 or lower. So we'll round this down and have a standard deviation of 8.04. By itself, that 8.04 doesn't really tell us very much. If we had another data set, we could say which one's more spread out, and whichever one had the higher standard deviation would be the one that's more spread out. Also, we're going to see the value of the standard deviation a little later on in class today when we start talking about the normal curve. I'm going to talk about this a little bit more before I have you try one, but before that, I want to see if you have any questions you want to ask about what we just did there. Okay. I'm not going to ask you this, but I can't help myself. I need to kind of tell you why this formula looks the way it does. So just kind of ride along with me here for a minute. What we're trying to do is figure out how spread out a data set is. And you can see here what we're doing is saying, okay, how far are your data points from the mean? What is the difference, subtraction, between your data points and your mean? And we have 3 data points we're going to divide by 3. So what we're looking for here is what is the mean difference between your data points and your mean? You know, and if you're thinking, okay, well, what's all the squaring and the square root then? How come we can't just find how far from the mean they are and divide by 3? Why won't we just do that? Here's why. Because if we just found out how far are they from the mean and then found the mean of those 3 numbers, if we did -8 minus 3, that's -11, plus 11, that would be 0. And we'd have 0 difference from the mean. Well, that's not true. All the numbers in here aren't the same as the mean. And so the reason for the squaring is to make the numbers positive. It takes those numbers, and instead of a -8, now it's a positive number, positive number, positive number. And so what we've done is we have made them all distances. We've made them all positive numbers with that squaring. Now, you might think, okay, why can't you just make them positive then instead of squaring them? And that's an excellent question. What squaring does is it emphasizes how far away a certain number is. Instead of just calling this 11, we're going to make it 121. We're going to really emphasize that difference. 3 only blows up to 9, but a number that's really far away from the mean blows up quite a lot. That's good. We're trying to show how far these are from the mean. And then finally, because we did this squaring, we've got to undo that at the very end, and we undo that by taking the square root. That's a great question, Zara. This is a really cool one that I don't know who thought it up and when, but figuring out how far data points are from the mean, I'm sure there was some trial and error involved, and they're like, okay, why don't we just do this? And they're like, wait, that didn't work. We got 0. We have to do something else. And then eventually you land on something that works for you. And so that's why it looks the way it does. Again, not going to ask you that. I just can't help myself but to tell you why it looks the way it does. Okay, now I'm going to have you practice by finding standard deviation for a data set. You're going to use this formula, and we'll see how it goes. I don't think this is necessarily easy right away. Be patient and careful as you go through it, and I'll give you a little time. Here goes. Find the standard deviation to the nearest hundredth for the data set 7, 13, 22. Remember, you've got x of 1, x of 2, x of 3, and you're going to need the mean. All right, that's all I'll say, and I'll just let you try this one. I'm optimistic. Oh yeah, and one other thing I wanted to say that I haven't said in a while is if you work through this and you have an answer and you don't see your answer listed over there, just pick the one that's closest to yours. Um, that way I'll know you've had enough time to work through it, and um, you can still certainly ask questions. You know, if you happen to get the right one by accident, that doesn't mean you're not allowed to ask questions. You absolutely still can. Um, you can expect to see standard deviation questions in homework, on quiz. It's one of those things that it's a complex looking formula that um, is a great thing if you understand what it is and how it works. Also, if anybody happens to be walking by and sees that on your paper, they might be very impressed. Um, and you should be too. If you're able to solve these correctly, I think you give yourself a pat on the back too. So if it goes well, that's awesome. If you have questions as we work through it, or, um, you know, once we finish, make sure you ask whatever you have. Let's go another 30 seconds on this. And if you need more time, you can let me know and I'll stretch that out. Okay, a little more time would be great. Yeah, very good, Edison. You definitely show it to him. I would. anytime things get this involved, you kind of want to show that off. And then what we'll have up next will be taking the standard deviation and showing another use of it rather than just which of two different data sets is more spread out. There's something more powerful than that we're going to use it for. And that's right around the corner for us. I think we'll go another 15 seconds. And then even if you're still working on it, you can kind of follow along what you're doing with what we're doing and, you know, see what you've got compared to what we've got. And wherever it doesn't line up, you can ask about that. Let's see what we've got here. Okay, very good. Not unanimous, but pretty darn close and strong agreement. I understand, Zara, that happens sometimes when you have to start over, that backs things up. Okay, well, that went extremely well. Let's start going through it. If you see something you're not sure of, make sure you ask. But I feel really good about how that went for sure. So I have x sub 1, x sub 2, and x sub 3 are my data points. I'm going to need the mean, so I'll go ahead and find that. And that's 7 plus 13 plus 22 over 3. 7 plus 13 plus 22 is 42 over 3, which is 14. So my mean here is 14. Now I can start plugging into my formula. My standard deviation is going to be the square root of, all right, x sub 1, which is 7 minus the mean squared, x sub 2, which is 13 minus the mean squared, and then x sub 3, which is 22 minus the mean squared, all divided by 3 because I have 3 data points. Not every data set will have 3. You might see 3, you might see 4. I don't think they're anywhere you would see 5, but maybe, and nothing bigger than 5. That would sort of be just overkill, I think, as far as how many data points to plug in. All right, as we simplify this thing, first we do our subtraction. We'll have 7 minus 14, that's negative 7 squared. 13 minus 14 is negative 1 squared. And then 22 minus 14 is 8 squared. And that's divided by 3. If you see anything that you're not sure where it came from, don't hesitate to ask. Standard deviation will be negative 7 times negative 7 is 49. Negative 1 times negative 1 is 1. And 8 times 8 is 64. We'll keep working here. All right, standard deviation will be, let's see, 49 plus 1 plus 64 is 114 over 3. We'll go ahead and divide that. And I get 38. And then I don't think anybody did it. No, nobody did it. The last step we need to make sure we do here is take the square root. Nobody forgot to take the square root, which is excellent. So we'll take the square root of 38 and get 6.1644. That decimal keeps going, but we were told to round to the nearest hundredth. So we'll find the hundredths place. Look one space to the right, that's 4 lower. So we'll round this down to 6.16. If you have questions on that, let me know. Outstanding work on the poll, everybody. That's terrific. Okay. All right. So I said at the beginning, the big thing today is a normal curve. So let's talk about the normal curve. Back when we were doing different types of graphs, we look at bar graphs, but we also looked at histograms, which were bar graphs where the bars were made with no space between them and they use continuous data. What you see there at the top, this is actually a histogram. The only reason that the little white lines are in there is because I wanted you to see that they are individual bars, not just one big blob with that shape. Imagine that they are just one, there's no space between the bars at all, that they run together there, and we have that shape. So we have a data set that takes on this shape when we graph it. And then instead of wanting to look at all those individual bars, we decide, you know what I'm going to do is I'm going to put a point at the top of each of those individual bars, and I'm going to connect the dots. And instead of looking at the individual bars, I'm going to look at that shape. And then once we have that line drawn in there, or that curve drawn in there, we take the bars away, we're left with this thing right here, and that's what's called the normal curve. We have a data set that when we graph the histogram, it looks like this. Draw in a curve, take the bars away, and now we're just looking at the curve that shows all that data. And that's the normal curve. A couple of things about the normal curve. Because it's symmetric, you can kind of see we have a symmetric distribution here, and in the middle, that's where the mean will be. So the mean and the median are going to be the exact same, right smack in the middle of this data set. And so far, we've used X bar to abbreviate the mean, and that's perfectly fine, but there's just the same way that we were able to use sigma for standard deviation, we can also use a Greek letter to represent the mean. And you'll see that sometimes too. And that Greek letter that we will use to represent the mean looks kind of like a lowercase u in cursive. It's got kind of a tail on the front of it. And that is the Greek letter mu. It's pronounced, mu. And so while it's perfectly fine for us, normal for us to use X bar for the mean, I want you to also realize that you'll see mu used for the mean of a data set also. And typically the reason that mu gets used is because if we're using a Greek letter for standard deviation, then it feels kind of right to use a Greek letter for mean. Nice thing is this is pronounced mu. This one is sigma. And the first letter kind of reminds us of what they represent. This one over here that starts with an S is for standard deviation. This one over here that starts with an M is for the mean. So that's what a normal curve looks like. Some of the important pieces there is we can call the mean mu in addition to x bar. Those are equivalent for our course. If you take a high-level stats class, they may make a distinction between those two. We're not going to. We're going to treat them as the same as each other. So what kind of data would make a normal curve? You know, we're looking for something that, what is it that's going to make a shape that looks like that? Well, one of the things would be standardized test scores. When we give a standardized test, what we expect is most of the scores are going to be right here in the middle. There's going to be a small number of really high scores and a small number of really low scores, but most of the scores are going to be in here close to the middle. And that's the kind of graph we would get if we made a histogram out of standardized test scores. We have our lower scores down here, we have our higher scores up here, and most of the scores are going to be in here in the middle, close to the mean. As we get further away from the mean, high or low, the number of scores gradually tapers off and gets lower. Same thing could be said of weights of newborn babies. There's a mean number in here for the weights of newborn babies. Most babies are going to be close to the mean. Sometimes you might get a really heavy baby. It's unlikely to have one way out here, but it does happen. It's unlikely, but it does happen to have a really light baby. And as you move further away from the mean, the number gets smaller and smaller and smaller. And that gives us normally distributed data. And then something we talked about briefly before, life of batteries. If we do a test and we see how long batteries last, most of the batteries are going to be in here close to the mean. As we get further away from the mean, the number of batteries is going to go down on both sides. And we'll have some batteries that just didn't last very long at all, and some that really lasted a long time. But not very many of those. Our histogram bars will be shorter, and that's kind of shown in the shape. So that's data that lends itself to the normal curve. The key ideas here is that the mean is in the middle. As we move away from the mean, the number of data points get smaller and smaller and smaller. Are there questions about that before we move on to something we get to do with the standard deviation? Fantastic. Okay, using standard deviation with the normal curve. So we see this shape here, that's our shape of the normal curve, and we can see that the mean is right here in the middle. And then what we've done is we have gone into this normal curve and we've cut it into sections. I cut a section here, and that is mu plus 1 sigma. What the heck? Mu plus 1 sigma, where did that come from? Well, hang on a second. We know mu is just the mean, and sigma is just the standard deviation. So this is whatever the mean is plus 1 standard deviation. The way that we might describe this location right here is 1 standard deviation above the mean. Using that same logic, we can go to the left side of the mean and go over here to this place where we've sectioned it off. And this is the mean minus 1 standard deviation. So what we would call that then would be 1 standard deviation below the mean. And then cutting it once is fine, but you know what? We're actually going to cut it several times. We are also going to draw in a line that cuts this at 2 standard deviations above and 3 standard deviations above. We're going to draw in lines that cut it at 2 standard deviations below and 3 standard deviations below. So if you're thinking, how do you know where to draw the lines? The mean goes right smack in the middle. And then this line gets drawn based on what is the standard deviation of this particular data set? That's how that line gets drawn. And this is the real power of standard deviation. Hang in there with me if you're thinking, okay, that's all fine. What's it? How do we use it? What does it do? That's next, I promise. And the power in this, the value in this, is the 68, 95, 99.7 rule. It's also known as the empirical rule. If you see the empirical rule somewhere in a problem, that means the same thing as the 68, 95, 99.7 rule. And so we have our normal curve there, and we have our lines drawn at the mean, 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. We also have lines drawn in at 1 standard deviation below, 2 standard deviations below, and 3 standard deviations below. And then here's where the 68, 95, 99.7 rule comes into play. When we have data that we know is normally distributed, standardized test, weights of babies, battery life, it fits this pattern right here. We know for sure, no questions asked, that 68% of the data is between 1 standard deviation below and 1 standard deviation above the mean. 68% of the data is between those locations. When we have an actual data set and we know the mean and we know the standard deviation, we can put actual numbers down here, and we're going to do that. But for right now, I just want to make sure to emphasize the point that between 1 standard deviation below and 1 standard deviation above the mean, that's where 68% of the data is. You probably know exactly what's coming next, and that's the idea that if we go out to 2 standard deviations below and 2 standard deviations above, that's where 95% of the data is. So if we were to shade all of that, what we're shading is 95% of the data. 95% of the data is between 2 standard deviations below and 2 standard deviations above the mean. Finally, last but not least, if we go all the way out to 3 standard deviations below and 3 standard deviations above, we're way the heck out there now. That's where 99.7% of the data is. If we go from 3 standard deviations below to 3 standard deviations above, we've captured 99.7% of the data. If you're thinking, oh, and this is why it's called the 68, 95, 99.7 rule. It's because between 1 standard deviation, 68, between 2 standard deviations, 95, and between 3 standard deviations, 99.7. A question you might have is, well, what about 100%? Where's 100% of the data? There is nowhere on here that we have 100% of the data. And the reason for that is, let's say we're talking about the weights of babies. While 99.7 of them are between here and here, there could be an outlier that's just one really heavy baby way the heck out there. And maybe he's way out here. I don't know. There's nowhere we can be sure that 100% of the data is. What we can be sure of is 68, 95, and 99.7. Let me know if you have questions on that before we take this and break it down even further. All right, terrific. One thing I'll say is, I promise I think you're gonna like and do really well with the problems we do related to the normal curve. Just sort of a heads up ahead of time. Okay, so let's focus in on the idea that we know for sure that 68% of the data is right here between 1 and 2 standard deviations below the mean. We also know that this normal curve is symmetric, meaning if 68% of the data is in here, then my question is, what percent of the data would just be right here? What percent would be just right there? And I'm going to let y'all tell me. Excellent, Zara. Genesis, very good. Outstanding. If 68% of it is between these two, then, and this thing's symmetric, then half of it's going to be in here. And what we can do is we can break down every region on here to see how much data is in each little piece. And that's what this picture does. We know because of the 68, 95, 99.7 rule that 68% of the data is between here. From there, we can gather that 34% is in each piece, and we can extend that out. 13.5% are in these pieces. 2.35% is in there. And then 0.15 is way the heck out here that, you know, goes beyond our 68, 95, 99.7 rule. This picture here will be extremely important for us when we solve problems. You will want to have this either memorized or written down somewhere. If you're thinking, how am I supposed to memorize that? Honestly, 34, 13.5, 2.35, 0.15. That's all you need to remember, because the other half is exactly the same. So it's only a few numbers. You're allowed to have a page of notes on the exam. You might want to have this on that page of notes. Okay, this picture is going to be important for us as we solve problems. So up next, let's look at the types of problems we're going to solve. "2,000 students took a standardized test that had a mean of 250 and a standard deviation of 50. And then we have a series of questions down there. I'm not even going to try to answer the questions yet. First, I'm going to draw my normal curve. Doesn't have to be perfect. There's my normal curve. What I'm told is that the mean is 250 and the standard deviation is 50. So with that in mind, I know that I can draw in my mean of 250. Now what I want to do is I want to section this thing off. I want to have 1, 2, 3 standard deviations above the mean and 1, 2, 3 standard deviations below the mean. Next, I need to figure out what numbers go in those places. I'll do the first one and then I'm going to ask you to help me out. So here I'm at the mean of 250. This is 1 standard deviation above the mean. Since the standard deviation is 50, that means that this spot right here is 50 higher than whatever the mean was. So that's going to be 300. Let me know if that 300 doesn't make sense and I can be more explicit. If that 300 makes sense, then my next question to you is, what numbers are going to go here? Like, okay, that's 2 standard deviations above the mean. So I went 50 to get there. What's going to be in the next spot? Really good, Zara, and I hope everybody's following you. Natalie, yes, if that's 300, now I need to be 2 standard deviations above the mean. So I went 50. Now I need to go 50 more and be at 350. Then I need to go 50 more and be at 400. Because that's 150 above the mean, this is 2 50s above the mean, and this is 3 50s above the mean. What number is going to go right here? 1 standard deviation below the mean. Very good, Zara, Emily, awesome. Riley, terrific. That's going to be 200, and I'm going to keep going the same thing all the way down. This will be 150, and this will be 100. And so now I've got my normal curve built. I'm ready to start answering questions. And just to sort of make sure we are all looking at the same thing, I'm going to take this normal curve, these labels that I just put down here, and I'm going to move those back to this picture, just so we can have an easier time answering our questions. We had a mean of 250. Standard deviation was 50, so I had to go up by 50 each time. And then on this side, I had to go down by 50 each time. All right, now let's start answering some questions. The first one says, what percent of the students scored above 250? The way that I'm going to answer this question is I'm going to go back and I'm going to look at my normal curve and I'm going to say, okay, what percent scored above 250? Well, here's 250. That's my mean. Above 250 is going to be to the right of there. So I'll just add up these percents and I'll have the percent that scored above 250. And let's see, that'll be 34 plus 13.5 plus 2.35 plus 0.15 is 50. I guess I should have known it was going to be 50%. This is right in the middle. Mean is the same as the median, so it's half or above 250. But the philosophy of finding the regions we need to count and adding those up, that's how we're going to solve these types of problems. So we wind up with what percent scored above 250? That was 50%. Our next question here is, what percent scored below 300? So I'll go back and I'll look at my normal curve. And I have, okay, here's where 300 is. That's one standard deviation above the mean. What percent scored below 300? Well, the scores that are below 300 are back here. So I'm going to have to add up all of these to figure out the percent that scored below 300. What I'm counting up is all of these bars in my histogram, really. And so I need to add all those up. And when I add all those up, I wind up with 84%. If you don't get 84, you're not sure where it came from, you can let me know. But I'll get 84% of the data is below 300. What percent scored between 150 and 250? Between 150 and 250. So I go back and I look, and here's 150 right here. There's 250 right here. And the percent that scored between those, that's this right here. So I need to add up these two numbers. 13.5 plus 34, that's 47.5%. So what percent scored between 150 and 250? 47.5%. How are we doing? These tend to go really well for students, but don't let me go so fast that you don't see what's happening. If you have questions you want to ask about how we got any of those numbers, you let me know. And what we did here was we were given the mean, we were given the standard deviation. Awesome. Those check marks are great to make this picture. And then taking the labels that I use down here in conjunction with this picture that tells me how much data is within each region, I'm able to answer the questions. All right. The next question, and there's an important distinction we want to make here, says how many scored above 350? The key distinction here is up to now our question said what percent, what percent, what percent. This one says how many, kind of like our box plot questions from Tuesday. Now it says how many. So the fact that 2,000 students took this test is going to play a role down here. So how many students scored above 350? First, I'll go back and here's 350. So what percent scored above 350? Make sure you count both of these. Don't just count the 2.35, count them both. We'll add those together. That's 2.35 plus 0.15, that's 2.5%. So we have 2.5%. If the question said what percent scored above 350, our answer would be 2.5. But it didn't. It said how many. So what we need is 2.5% of those 2,000 students. We're going to write 2.5% as a decimal. If you don't remember how to write 2.5% as a decimal, we're going to divide it by 100. So if you do 2.5%, if we divide that by 100, we'll get the decimal value. It's a really small number, so sometimes that can be a little bit troubling, but we get 0.025. We've converted that percent into a decimal. And so now what I have is 0.025 of is a word that tells us to multiply 2,000. So we'll multiply those together, and I get 50. So 50 students scored above 350. If you wanted to identify your top scorers, there were 50, there were 50 students over here that were in the top 2.5%. Oops, keep hitting the wrong button. Good, very good, Zara. And we have one more question on here, and what it says is, how many scored under 150? Yes, we never see 100% of the data. That's correct. Now, our normal curve, this 0.15 out here, that's beyond 3 standard deviations above the mean. So this 0.15 takes care of everybody all the way up to infinity. So anything that's possibly out there to the right is included in that 0.15. The 2,000, Stephanie, came from the problem. We were given that in the problem. Don't understand what, Escadar? Oh, we haven't even started that one yet. we were still talking about above 350. We haven't started working on under 150 yet. Okay, well, let me see if I can help a little bit here. Oh, I see what you're saying. It's the how many that's giving you trouble. The how many, now we're not saying what percent. Our answer isn't look at this chart, add up the percents, and report that as an answer. Now the question says, how many students scored that? And so we want to know, out of these 2,000 students that took the test, how many of those individual people, so not a percent answer, but how many people scored above 350? The way we find that is we first use our picture to figure out the percent that scored above 350. And we can see here that 2.5% of the students scored above 350. If that doesn't make sense, you let me know. But 2.5% of the students scored above 350. If the question said what percent scored above 350, we'd be done. But this question said how many? And so we have to figure out what is 2.5% of 2,000. We know it was 2.5%. We know there were 2,000 students. So what is 2.5% of 20,000? And to do that, we change 2.5% to a decimal. Of tells us to multiply 2,000's number we were given in the problem of how many students there were. And to find out what is 2.5% of 2,000, we just multiply 0.025 times 2,000, and that's where the 50 comes from. Hopefully that helps. If not, we can work on those maybe after we finish the rest of our content here. Converting a percent to a decimal may be something that you haven't done in a long time. All you need to do is divide it by 100, and that works. Other people like to memorize, just move the decimal 2 places to the left. That works too, as far as converting a percent to a decimal goes. The last question on here that we didn't get to says, how many scored under 150? And we go back and we look at our chart and we say, okay, well, here's 150. The percent that scored below 150 is 2.5%. Oh, well, that makes sense. Whatever happens on the right of 2 standard deviations above the mean, because this is symmetric, the same thing's going to happen to the left of 2 standard deviations below the mean. And so here again, it's 2.5%. 2.5% of 2,000, we get the exact same answer here. 50 students scored above 350, 50 students scored under 150. I want you to try some of these, so here goes. 500 students took a standardized test that had a mean of 26 and a standard deviation of 3. I have two questions for you that I want to ask here, and the first is, what percent scored between 23 and 29? And the second is, what percent scored above 29? These are both asking for percents, not how many's. I'll give you a chance to try this, and then we'll work on it together. I'll set up a poll for this. Got it. Yes, the scores and the people are different. The number of people that earned a certain score is what we were looking for. Yeah. So I'm going to leave this here for a minute. The mean is 26, the standard deviation is 3, and we want to know what percent scored between 23 and 29, what percent scored above 29. I'll move this back to the picture of the percentages in just a minute, but I want to make sure you have what you need from this page before I do that. All right, so there's a poll for that one. I'm going to go back to the page that had the percentages on it for you, keeping in mind here that the mean is 26 and the standard deviation is 3. Yeah, let's see, what's the question? It did? Oh, well, that's odd. I will put it back. Huh, maybe it didn't like when I erased that page. Sorry about that. That means you're close to done though, which is really good. All right, we'll try that again. So what percent scored between 23 and 29? What percent scored above 29? And our mean was 26 and our standard deviation was 3. We'll go another 20 seconds on this one and then talk about it. See where we are on this one. All right, very good. Again, very good. Polls have gone great today. That's awesome. Okay, so let's talk through this thing. We were told in this particular problem that our mean was 26 and our standard deviation was 3. So we can go ahead and label our picture. 26 is the mean, and then we have to go up by 3 more, up by 3 more. On the left-hand side, we'll go down by 3 again, and down by 3 again. And so we can see the scores down here that are 1, 2, and 3 standard deviations above the mean. We can see the scores that are 1, 2, and 3 standard deviations below the mean. The question we were asked in this one was, let me pop that up. What percent scored between 23 and 29? Okay, so we go back and we look at our picture and we see that between 23 and 29, that's between 23 and 29, that's right here. So that's those two pieces, which is 34 plus 34, 68%. And honestly, that's just straight 68, 95, 99.7 rule, in that between one standard deviation below and one standard deviation above, we know we're going to have 68% of the data. The second question, what percent scored above 29? So we'll go and we'll find 29. That's here, one standard deviation above the mean. What scores were above 29? That's all these, which would be 13.5% plus 2.35% plus 0.15%. Adding those together, we see that 16% of the scores were above 29. Very good on the poll. If anybody has questions you want to ask about that, go ahead and let me know. Okay, those are the type of questions you can expect to see related to the normal curve. Once you've got your picture drawn and you've got your labels in place, it's really just about identifying the appropriate regions that we're counting. Okay. A student scored 400 on a standardized test that had a mean of 250 and a standard deviation of 50. What would you expect this student to score on a test that has a mean of 100 and a standard deviation of 10? Now, at first glance, you might think, well, how am I supposed to know? I mean, okay, scored 400 on a test that had a mean of 250 and a standard deviation of 50. And he's going to take another test. Well, the idea here is they're over the same content. And so we expect the student to do just as well on the second test as they did on the first one. We're going to be able to use these results to predict what's going to happen here. And this is how we can do it. We were told that that first test that they took had a mean of 250 and a standard deviation of 50. So let's take a look at that. A mean of 250 and a standard deviation of 50. So that would be 300, 350, 400. Let me know if you see something that you're not sure where it came from. What we did is do our mean and 1, 2, 3 standard deviations above the mean. On that particular test, that student scored 400, which is right here. Their score was 3 standard deviations above the mean. So when they take the second test, we would also expect them to score 3 standard deviations above the mean. Now, on that other test, the mean was 100 and the standard deviation was 10. So on that one, the mean was 100 and the standard deviation was 10. So 110, 120, 130, Because they scored 3 standard deviations above the mean on the first test, we would expect them to score 3 standard deviations above the mean on this second test, and we would expect their score to be 130. So basically, we were able to use how far were they from the mean on the first test to see what do we expect them to score on the second test. Let me know if you have questions on that. At first glance, it feels like a question that we're not going to be able to answer. Turns out to be relatively straightforward once we draw a picture and see what it is we're looking at. Excellent. All right, here's another. Tom scored 80 on a standardized test that had a mean of 100 and a standard deviation of 10. Jerry scored 90 on a standardized test with a mean of 105 and a standard deviation of 5. Who scored better? Your instinct here might be well, I don't know, Tom scored 80 and Jerry scored 90, so Jerry did better. But there's certainly more to it than that. One of them may have been taking a much harder test. And so these scores and means and standard deviations are how we're going to figure out who scored better. We're going to draw a picture for Tom. And let's see, Tom had a mean of 100 and a standard deviation of 10. And he scored 80. I can see that he scored below the mean, so I'm going to go ahead and just draw this side. And so Tom's score was right here at 80. He was 2 standard deviations below the mean. Let me know if you have questions. You probably can anticipate what's going to happen next. We're going to draw a picture for Jerry. Our picture for Jerry had a mean of 105 and a standard deviation of 5. Standard deviation's 5. We can see he scored 90, so we can draw this side. Let's see, standard deviation was 5, so that'll be 100, 95, 90. And by looking at that picture, we can see that Jerry's score is 1, 2, 3 standard deviations below the mean. Well, being further below the mean would be a worse score. So Jerry being 3 standard deviations below is worse than Tom, who was only 2 standard deviations below. So the question here of who scored better, well, Tom scored better because he was only 2 standard deviations lower than the mean. Jerry was 3 standard deviations below the mean. So Tom did better. Let me know if you have questions on that one.